Good day, everyone. Today I will continue with the final value theorem. We know that the Laplace transform of the derivative of f with respect to time is given by s fs minus f of 0 plus. This result has been proved in my previous video, which is Laplace transform part 2. So we will follow the same sketch of proof of the initial value theorem. Instead of taking the limit to infinity of the Laplace of f, I will take the limit when s goes to 0. So the limit of the left-hand side will be equal to the limit of the right-hand side, which gives limit of sfs minus f of 0 plus when s goes to 0. Exponential minus st at s equal to 0 will be 1. This implies that the Laplace of the derivative of f with respect to time when s goes to 0 will be equal to df over dt dt, okay? Because the exponential here will be replaced by 1 at s equal to 0. So the value of this integral is trivial. It will be f of infinity minus f of 0. So it is a limit of ft when t goes to plus infinity minus f of 0 plus. Okay. Now, the limit of sfs minus f of 0 plus, okay, when s goes to 0, will be equal to this. Now we have f0 plus from the left-hand side, and we have f0 plus from the right-hand side. They will be simplified, and we will be left with the limit of ft when t goes to plus infinity equal to the limit of sfs when s goes to 0. This is one of the interesting results of Laplace transforms. It means if I am in the frequency domain and I have the Laplace transform of ft, noted fs, I can know what is happening or what is the limit of ft when t goes to plus infinity. So the initial value theorem indicates the value of ft at the origin at time t equal to 0. The final value theorem gives us an information about the behavior of ft when t goes to plus infinity. Okay, it means we don't need to evaluate the inverse Laplace transform. We need only fs, which is the Laplace transform of ft. And by composing the limit sfs when s goes to 0, we shall be able to know the limit of ft when t goes to plus infinity. Let us expose these simple examples. So the Laplace of the step function of terminal value equal to 1 and step time equal to 0 is 1 over s, okay? Now, assume that I know 1 over s, okay, which is the Laplace of ut, and I am interested in getting the limit of the step function when t goes to plus infinity. We know in advance that the step function has a limit equal to 1 when t goes to plus infinity. So if I will compose now limit of sfs, where fs is 1 over s, I will get 1. Okay? It means if I know this, only this, without necessarily knowing the shape of ut, if I will multiply it by s and tend s to 0, I will get 1. I know that the step function will have a terminal value equal to 1. The Laplace transform of the sine bt is given by b over s2 plus b2. So now if I will apply the initial value theorem, I know that the function at time t equal to 0, it is the limit of sfs when s goes to plus infinity, which is the limit of this function and consequently the limit will be equal to 0, and we know that the sign of 0 equal to 0. So this is a demonstration of the initial value theorem and the final value theorem through basic functions that are the step function and the sine function. Time transformation. Time transformation, it means that I have some transformation which is on the argument of the function f. So here I have at minus b, and I will call tau to be at minus b. Okay, so I will call the signal f sub t to be the transformed signal from ft. Okay, and I will note fs to be the Laplace transform of ft. I would like to get the Laplace transform of ft, which is the transformed signal through this transformation, time transformation, function of the Laplace transform of ft. So the Laplace of ft, I will call it capital F of t of s, which is the Laplace of at minus b times u of at minus b, because we know that in advance that the Laplace is existing from 0 to plus infinity. It means when the argument at minus b is positive. This is why we are multiplying the function by the step of argument at minus b. Here we apply the definition of the Laplace, and then I will make a change of variable. I will put tau to be at minus b, and then I will express t in terms of tau, and then I will calculate the differential of time function of the differential of tau. So we have dt equal to 1 over a d tau. The limits will not change except at 0. So at time at t equal to 0, I have tau equal to minus b. At infinity, I have infinity. So this is why we are seeing minus b to infinity plus infinity, f tau u tau exponential minus s, and I will replace the t by this, which is tau plus b over a. d tau over a, it is dt. Okay, so now I can make an exponential which is free from tau outside, which is exponential minus sb over a divided by a, this factor. Integral of f tau, u tau is 1, and I will have exponential minus s tau or s tau over a d tau. Okay, so we see clearly that we have the stem, which is here, and the integral expression here, it is nothing but the Fourier transform of ft evaluated at the argument s over a. Okay, so as a conclusion, if we have a transformation like this, transformation in time that make here a dilatation or a compression of the signal ft, and the b will play the role of shifting in time. So we can shift and compress or make a dilatation of the signal through an appropriate choice of the coefficients a and b. Okay, so delay, we see the appearance of an exponential. Okay, and compression, we see some factor here s over a. Okay, so you see here it is a times t, and here we have 1 over a times s, and this is why we see the inverse behavior in the frequency domain. It means if a is greater than 1 over a will be less than 1. Okay, and here we can compress or make a dilatation of the spectrum depending on the value of a. Transforming the integral to prove this result, we have many options. Okay. So this is one option here. So we will define the function gt to be the integral 0t f tau d tau. And then I will compose the Laplace transform of gt. So I will have the signal gt times the exponential minus st dt under the integral 0 plus infinity. I will integrate by parts. So I will put u to be this, dv to be exponential minus st dt. Then if I will differentiate, I will have du equal to ft dt, and the v will be exponential minus st divided by minus s. By integration by part, I will have two terms. Okay. So this term is 0 because exponential minus st at infinity is 0. And at 0, if I will replace the time by 0, I will have integral from 0 to 0, I will have 0. Okay, so I will get 1 over s. It means this term remains, and I will have 1 over s fs. So the term which is here, it is by definition fs. Okay. How about the convolution of two signals? This is one of the important properties of the Laplace transform, because any signal which is tackling a dynamical system, we have this phenomena of convolution of what? Of the input through the impulse response of the system. So this will be used extensively in studying systems and signals in the frequency domain. So we will prove here that the convolution of two signals f1, f2, so the star stands for the convolution products, results on a simple multiplications of the two spectrums of f1 and f2. The proof starts from here. We will define integral 0 plus infinity of what? Of f1 star f2. So this is f1 star f2 exponential minus st dt. Okay. So the time t so here we have d tau, and the tau is between 0 and t. Okay. And the time t is between 0 to plus infinity. So here we can change the order of integration. We can say tau from 0 to plus infinity, and the time between tau and plus infinity. So the domain t between 0 to plus infinity, and the tau between 0 and t, it is exactly the same domain, tau between 0 to plus infinity, and the time between tau and plus infinity. Okay? Now, when we arrive here, okay, and you see here that we have changed the order of integration. So here we have d tau dt, and here we have dt d tau. Okay. Now I will define a variable z to be t minus tau. Okay. So the integral from tau to plus infinity f2 of t minus tau exponential minus st dt will be f2 of z exponential minus s, and I will replace the t by z plus tau. Here I am integration with the dz, because dt will be equal to dz when tau is constant. So I can make the factor exponential minus s tau here, because it is not dependent on z, outside the integral, and I will keep 0 plus infinity f2 of z exponential minus s z dz. And this is exactly the Laplace transform of f2t. Okay, right. So now I have a factor exponential minus s tau, okay, multiplied by f2, multiplied by f1, and then integration with d tau, with respect to d tau. Okay. Since f2 is not dependent on tau, it can go outside the integral. And here I will have integral 0 plus infinity f1 of tau exponential minus s tau d tau. And this is exactly the Laplace transform of f1 of t, which is f1 of s. And at the end, we will have a product of f2 times f1, which is the results shown above, okay, here. The multiplication property is also important. I will not give a proof here, but I will leave it for the students to have one possible proof. We can prove it with many ways. So now I can say that if I have a Laplace, okay, of the inverse Laplace of f1 f2 will be the convolution of f1 f2. Okay, so I will leave this. It means proving the convolution in the opposite sense. Okay, it means prove that the inverse Laplace transform of f1 f2, it is exactly the convolution product of f1 t f2 t. Okay, shifting in the S domain. The shift in the S domain, or the shift in the frequency domain, results when we multiply the function in time by an exponential function of time. The proof is too easy. We have just to compose the definition of the Laplace of this function, which is this. And then we will gather the two exponential, and it appears exactly as the Fourier transform of S minus a by definition. So as an example, if I have an exponential function minus at times ut, when t is positive, we know that the Laplace transform of ut is 1 over s. If I will multiply it by an exponential function, I will get a delay in the frequency domain. You see here that the sign has been changed. It means if I have minus a here, I have plus a here. Okay. How about if I will do a delay in time? In this case, I have ft minus a. So a, it could be a positive or a negative real. Here we see the duality. Delay in time results on a multiplication by an exponential function in the S domain. And we have another remark that the sign is preserved. Means if I have here minus a, I will have also minus s here, which is not the case when I have multiplied the function by an exponential function. And we have the shifting in the time domain, okay, results on an exponential with the same minus a here that I have in the delay of the function f. So now, if I will start from the definition of the Laplace, I have ft minus a exponential minus st dt under the integral 0 plus infinity. Okay, I will make a change of variable t minus a to b tau. Then the limits will change according to this change of variable. Okay. And then I will have exponential minus a s, okay, integral 0 plus infinity f tau exponential minus s tau d tau. Okay. But we have just here a remark. You see here that this limit minus a, okay? And here I have what? I have 0. Assume now that a is positive, okay? If a is positive, from the interval minus a to 0, the f is 0, okay? This is why we will have 0 to plus infinity, okay? F tau exponential minus s tau d tau, which is exponential minus as times the Laplace transform of ft. Consider now this simple first order differential equation with respect to a variable y. We will assume that y is the variable and the u is something that we know is a function which is dependent on time. The question is using the Laplace method to solve the ordinary differential equation for null initial conditions. It means y of 0 equal to 0 and ut being the step input. What I have to do, I will compose the Laplace transforms in both sides of this. So here I will compose the Laplace of the derivative, and here it remains the same, and here it remains there is I mean that I will just replace yt by ys and ut by us. So this is what I am seeing here. Okay, since I have an initial condition equal to 0, so I don't have here minus y at time 0 plus. So this is why I am seeing only the term 2sy ys plus ys equal to kus, okay, where ys and us are the Laplace transforms of yt and ut respectively. Us is equal to 1 over s because we have considered a step of amplitude 1. And then I can solve here with respect to y. When I will substitute us by 1 over s, I will get this function in s. So this function in s can be split into two terms like this. And we know that this part, it is k times ut. It is k times ut. And this one, it is a factor. Okay, I can put tau in factor, and here 1 over tau. Okay, and then I will have what? A delay in the frequency domain. It means multiplication by an exponential in the time domain. So here I am using the property of delay in the frequency domain, of shifting in the frequency domain, to get the inverse Laplace transform, which is exponential minus t over tau. So here I am not writing ut because I am just specifying here t greater or equal to 0. In this exercise, I am asking for the inverse Laplace transform of this function hs, defined as a ratio of two polynomials in S. When we apply a step at the input, it means xs equal to 1 over s. So now the output is written as x times h, which is given by this function. Now I will use the method of decomposition of rational functions in order to put ys as a sum of simple rational functions where I can deduce easily their inverse Laplace transform. So here we have s factor something, so we have 1 over s2. It means that we have root double at s equal to 0. And we have two roots s equal to -1 and s equal to -2. So this way s can be decomposed as what? As a sum k3 over s plus 1, k4 over s plus 2 to get, okay, the simple roots here. And here I have a root which is doubled. So this can be decomposed in the following form. It means I will start from s power 1 until s power 2, because here I have a root of the denominator s equal to 0 double. Okay, so I have a root of multiplicity equal to 2. So now k3 and k4, okay, are obtained directly from the formula of simple roots, as I have indicated in my previous video. And K1, K2 are obtained from the differentiation formula of decomposition of rational functions. So this gives these values. And at the end, I can expand ys as follows. You see that I have simple rational function. We know that we identify this one to be minus ut. And here exponential minus t times 4. And here exponential minus 2t multiplied by the coefficient minus 3. And here we have the ramp function, okay? So yt will be 2 times t minus 1 plus 4 exponential minus t minus 3 exponential minus 2t. And here we have to say t positive, or multiplied all this term by ut. I invite the students also to test the efficiency of the comments of MATLAB for getting the Laplace and the inverse Laplace transform. So this is a short program in MATLAB that helps you in getting the inverse Laplace transform by defining h as given to you, without forgetting the symbolic declaration of s and t. So here we define h, here we define the x, here we define the output, which is the product of h times x, and y, I Laplace, it means calculate the inverse Laplace transform of y. To get the Laplace, we put Laplace of something, Laplace of a function which is dependent on time. I am just exposing here an important results related to periodic signals, but I will not give the proof here in this video. I will return back to periodic signals when I will tackle problems of Laplace transforms, and I will focus on some periodic signals and how can we get the Laplace transform of periodic signals from the Laplace of the generating function. Now, if ft is a periodic signal, it means it is repeating itself. It has the same value. If I have ft plus capital T, where the t is the period of ft, t greater or equal to 0. So the results that we are showing here, it means the Laplace of the periodic function ft, it is 1 divided by 1 minus exponential minus st, where the t is the period of ft, times f1 of s. What is this f1 of s? It is integral from 0 to t. Here pay attention, it is not 0 infinity, it is not the Laplace transform of ft, it is just a short integral from ft from 0 to t is like I am calculating the Laplace transform of the generating function of f. Okay, so it is 0t ft exponential minus st dt. In this table, we are showing the most important signals that we face when we have solutions of ordinary differential equations, linear ones, like time, t power n, exponential function, sine and a cos, combination of exponential with a sine and a cos, time times a function of sine times a function of cos, etc. Okay, so I will invite the students to verify all these tables using the properties of the Laplace transform, or by the direct use of the definition of the Laplace. In this table, also I am summarizing the most important properties of the Laplace transform, starting from the linearity, differentiation, nth differentiation, integral, delay in time, delay in the frequency domain, initial value theorem, etc. Okay. I have also a set of Laplace transform of when we have a combination of exponential functions with a sine and a cos. Okay, and when we study linear systems, specifically second-order systems, we may face solutions in that form or a combination of solutions of that form. Okay, so I also invite the students to revise or see attentively these transforms, okay, and to redo, okay, or trying to redo or getting the same result as indicating in this table. Right. So this is an exercise that I am proposing for the student to find the Laplace transform of Vt using the Laplace properties. Okay. So one of the simple solution, I will give you just a hint to do it. Okay. So you can use the differentiation property of the Laplace, because here we see that we have a line, okay, of equation t, and here we have what? We have minus t plus 2, okay, minus t plus 2. You see that you can use the properties of tut, which is multiplication by a time times the step, so you can get easily the results, or use the differentiation property of the Laplace. You can differentiate this signal. From 0 to 1, you will get a constant equal to 1. And from 1 to 2, you have what? You have a slope equal to minus 1. So here, by differentiating Vt, you have a double pulse, okay, of 1 minus 1, okay? If you continue the differentiation of order 2, you will get the Dirac function. And you know that a Dirac function has a Laplace transform which is equal to 1. Now you can use the property of the differentiation to return back to the Laplace transform of Vt. Here it is another exercise which is similar to the previous one. You can use the differentiation properties in order to get the Laplace transform of Ft.